Hello, welcome to Points of Topology Part 2 NPTEL NOC course. It's a third lab session. This is Shavik working on Cosmic Mantras. So this is the third lab session of this course. So there are basically 9 lab sessions left. So this session shall go from 6 to 8 p.m. in each Sunday. Okay, so before studying further, please let me know, do you have any question or any doubt from the previous session? Well, there is one student, Mr. Mustak. Can you please confirm whether I'm audible and is the screen visible to you?
Yes,
Okay,
the audible and the screen is visible too.
okay. Thank you, Mustak, for the
No, I have no
confirmation.
question.
Okay, thank you, Mustak, for the confirmation. So we shall start today's lecture. Okay, okay. So okay. So in case you have any question, please unmute it so let me know because while writing, I can't see the screen really. Okay, the first question. I mean, so okay. So we are going through compactness. The first question is that. First question is, let f(x) to y be continuous such that the domain is compact and codomain is Hausdorff. Show that f is a closed map. That means what? That means you have to show that f maps a closed set to a closed set, right? This is the thing you need to show, correct? So yeah, so that's the thing you need to show. So please think about it, take your time, let me know. That means what? You need to start with a closed set in the domain. Let's call it f. So the hint is as follows. Start with a closed set f subset of x. You need to show that f of f is closed in y. Okay, so that's what you need to do. So please take your time, think about it, let me know. Mustak, please take your time, think about it, let me know the answer. So there is one more student. So there is one more student has joined. Let me explain the question. This question tells that suppose f is a continuous function from x to y such that x is compact and y is Hausdorff. We need to show that f is a closed map. So basically here the Trick is to start with a function, start with a closed set f, which is a subset of x, and we need to show that its image is closed to y. Is the question clear to Rahul?
Yes, sir.
Okay, so please try to do it by yourself. Take your time and let me know. If you have any question in between, please unmute yourself and you may start ask the question. Rahul or Mustaq, anybody are able to figure out how to attack this problem or solve this problem? Basically, for this problem, you have to use the properties of compactness, properties of closed sets inside a compact space. Those small useful properties you have to use. So please try to do it. Mustaq or Rahul, anybody? How to solve this problem? Okay, so let me explain. So this question should not take too much time. Okay, okay. So the argument is as follows. Basically, what we need to do. See, we have a subset of X closed, right? Now it is known that closed subset of compact space is compact. That means F is a compact. That means F of F is also compact. Since continuous image of compact set is compact. Now f of f is a subset of y, and y is Hausdorff, and f of a is being compact. This implies what? This implies f of f is closed. Is the argument clear? That means in a Hausdorff space, compactness implies closed. I mean, in Hausdorff space, compact is equal to closed. Okay, so this is the theorem which you have seen in the last class, or maybe the first class. Anyway, so that's the thing. Is the argument clear? Please let me know. Is the argument clear, Rahul and Mustaq? Please let me know.
Yes, sir.
Okay, thanks for the confirmation. Okay, so now we can go to the next problem. The next problem is, okay, the next problem is as follows. Let y be compact. Then show that the first coordinate projection map is closed. So this question says that we have the first coordinate projection map x cross for the x comma y going to little x. The first coordinate projection map will be closed if y is compact. So yeah, so please try to review yourself. Basically, for this you have to start with a closed set and you have to exploit the properties of compact sets. Okay, so that's the thing you have to do. Okay, so think about it, take your time, let me know.
Sir, can we do like this? Inverse image of open set we get. Hello.
Let me tell me.
Hello.
Yes, tell me, sir, tell me.
Sir, can we take like this as x comma y tends to projection to x? So we take an arbitrary element x in x as the image, and we took the inverse image mm, x comma capital Y, x into capital Y. So we get the x is the single
One
element.
minute, one. You start with an arbitrary open set, right? Is it?
Yes.
But you need to show it is closed map, right?
Yes. So as Y is compact, then inverse image is closed.
No. What to, so I mean by closed map, what does you need to show? By closed map, what you need to show actually? No need to hesitate. You can tell. By closed map, actually, what you need to show? No need to hesitate. Please tell. Whenever we say some map is closed, actually, what we need to show?
I'm not getting that point.
So the question tells that show that pi 1 is a closed map, right? So by
Yes.
so basically what we need to prove actually?
We need to show x is closed.
No, by closed, so that is a x is a set, right? But here is a closed map. Basically we need to show that pi 1 of any closed sets is closed in y in x, where f is a closed set in x cross y. So closed map means it sends a closed set to another closed set. Is it clear?
Yes, sir.
Definition of closed set means it sends one closed set to another closed set. The image of a closed set is a closed. That's what by closed set we mean. Similarly, open map means what? It sends open sets to open sets. Is the
Yes.
definitions clear?
Yes, sir.
Okay, now please try to, yes, now, okay, so now please rethink the argument and tell me. No need to hesitate. Whatever the argument you is coming in your mind, you can say. Okay, please think again and let me know that. Okay.
Okay, sir. Can we do like this? As f is closed set in x into y. So we have to show pi 1 f is closed in x. So we take a sequence x d in f.
So are you going to give an sequential argument? Is it?
Yes, sir.
Okay, but sequential argument is valid in case of metric space only, right? In topological space, closeness implies sequential argument, but sequential criteria does not necessarily imply the set is closed. Okay.
It
That is
means
why,
here we cannot go by sequence.
yes, correct. Generally, you cannot go by sequence. You have to use some other process or other. You have to do some other way, or sequence will not work here. Please rethink again for a few more minutes and let me know. Otherwise, I will explain. Okay.
Okay, sir.
Okay, are you able to figure out any argument?
No, sir.
Okay, let me explain. So basically, so in this argument, we start with f, which is a closed in x cross y, right? Okay. Now, so for sake of understanding, this is our f. So by definition, x, the complement of f in x cross y is open. Correct? So there is nothing much to explain. Okay. So now what are doing? We are taking a x outside of f. Sorry, it's not x, it is basically x cross y. outside of F. So this is some x cross y. Okay.
Yes.
Now, since F is uh, open, so that implies what? Uh, that implies there exists a tubular neighborhood U of x such that U intersection F is empty. So by this what I mean is that we have here x cross y, here we have the point x. Then we shall get a neighborhood like this, which contains the point x cross y of course, and this neighborhood lies outside of capital X. Okay, is this line clear? Yes or no? First tell me.
Sir, I have a question. Why we taking tubular neighborhood? Why can't we take a single straight line?
Because we are in x cross y, correct? In x cross y, for example, so this is x cross y, okay?
Yes.
So suppose this is the neighborhood of x, this is the neighborhood of x, and this is the neighborhood of y, okay?
Okay, sir. I understood now.
So that is why this tubular neighborhood is coming to picture. I mean, it is just a neighborhood, but for sake of explain, for sake of, I mean, it's a term that,
Convenience.
I mean, tubular neighborhood is just a term, so there is nothing much to be about tubular. It is just a matter of picture only. So it is nothing more than that. It has no not much significance. Okay. Okay, so we shall get a tubular neighborhood around the point x comma y, which contains u, so that u intersection f is empty. Okay. This is nothing but there exists an open set V around X such that pi 1 inverse V intersection F is equal to empty. Is it clear or not? First tell me. That means what we're saying is that we shall get some V around X. Okay, around X we have some neighborhood V whose pi 1 inverse. This is pi 1 inverse of V. Okay, this is basically nothing but pi 1 inverse of V. This pi 1 V inverse of V, this lies entirely inside within U, so that its intersection with F is equal to empty. Is it
Clear,
clear
sir.
or not? First tell me.
Yes.
Okay,
Clear, sir.
just hold on. Okay, so okay. So that means what we are getting is that for each x belongs to x, there exists a neighborhood Px containing x such that pi 1 inverse V is equal to empty. Okay. Now consider the set. So we have pi 2 inverse till now. This is V, this is x, this is V, and we have some pi 2 in pi 1 inverse of V. 1 minute. Okay. Now what we are doing, what shall we shall do? We shall take consider the pi 2 of, see what is the next obvious step. We have given that y is compact, correct? And we get an open strip coming as a tubular neighbor of the point x plus y, namely pi 1 inverse of V. In order to use the compactness of y, what will be the next obvious step? Tell me. In order to use the compactness of y, what will be the next obvious step?
We have to show the The inverse image of V2 intersection with F not phi.
that sorry, repeat again.
The inverse image of V intersection with F is not phi.
I mean, that is already we have, right? We have this equation, correct? So there is nothing to do. So basically, the in order to use the compactness of y, we have to come up with an open cover of y, correct? But till now we are getting like for each point x, we shall get a neighborhood vx around x. That means this vx forms a this vx forms a open cover of x. But we need to go to open cover of y, correct? So what we'll do? We'll consider pi 2 of pi 1 inverse of vx. That means whatever the open set we have, we are taking basically the projections of all this. Okay. So this collection, sorry, this collection pi 2 of pi 1 of vx, this collection forms an open cover of x. Is it clear or not? Please let me know.
Sir, we are taking pi 2 as the horizontal way.
Pi 2, the map pi 2 is the second coordinate projection. That means pi 2 of x cross y to y, and the map is x y equal to y. So this is the second coordinate projection of pi 2.
Okay.
So inverse image will be the horizontal strip intersection. So till now we have pi 2 of pi 1 inverse vx as the open cover of x. So please tell me whether up to these things are clear or not.
Clear, sir.
Okay. So in that case, so now given y is compact, correct? It is given. That means this open cover has a finite subcover. So we can write y is the union of pi 2 of pi 1 inverse of vx. Sorry, vxi I should write. So this open cover is a finite subcover pi 2 of pi inverse of this. Okay. Now, so we come up with certain vi's, vxi's, I mean, which basically this is nothing but we have this, and we have few points, and around those points we have few neighborhoods, and we then consider the strips, and we are taking the pi to inverse. Okay. Now what we are doing is that take v to be intersection of vxi. Now claim is that v intersection f is empty, that is the target. Okay. Now this step v intersection f is empty shall follow from the construction. So this part please try to figure out by yourself. If not, then I will explain. Okay, please take your time.
Sir,
Yeah, tell me. Yeah, tell me.
sir, as each Vx intersection with F is phi,
Hmm.
so any arbitrary intersection with F is phi.
Yeah, correct, correct. Then
So we can directly claim the finite intersection of Vx intersection with F is phi.
correct, correct, right, right, absolutely correct. Very good. So this, so this problem is now over, right?
Yes, sir.
Okay, good. Okay, so the next problem is, hold. Next problem is, let tau and tau prime be two compact Hausdorff topologies on X. Show that if tau sub of tau prime, then tau equal to tau prime. Basically, here I wanted to show, suppose on a set X we have two topologies tau and tau prime. One is, both are compact Hausdorff. You basically need to show that if one contains other, then basically both has to be equal. Okay, so this is what you need to show. So yeah, so please try to do, then I will give hint. Anybody able to figure out how to approach this problem? Is there anybody able to figure out this argument? Okay, so let me give one more hint, which actually may be useful. Okay, so one minute. So basically, in order to show, basically, we need to construct the identity map identity from x tau prime to x tau, x going to x. First, this identity is a continuous map. First, this identity map for x tau prime to x tau, this map is this. You first need to show that this is a continuous map. Then only we can further apply the continuity things on the compactness. Okay. So first try to show that identity is continuous map. Basically, target is first show the identity continuous map. Secondly, identity is a homeomorphism.
So continuity is so direct by definition as every element
Why
pre-image
continuity? By
because
continuity, what you need to show? You need to show that inverse image of open set is open, right? So tell me why it is direct.
because every took any element in tau, then
Uh,
which also contain in tau prime. So every element in tau is contained in tau prime, so open in tau prime.
Correct,
So
correct,
continuity is
correct.
direct
So it is
by
continuous.
definition.
Correct, correct. Now show that this map is a homeomorphism. That means what? Either you need to show that the reverse map, that means x comma tau to x comma tau prime, that map is continuous, or you need to show this identity map is a closed map, or it is an open map. So I mean it's a bijective continuous. In order to show homeomorphism, you need to show either it's open map or it is closed map. Anyway, you need to show this, right? So now try to show those things. I basically show that basically you need what is that? Basically you need to show that identity is a closed map. It sends closer to closer. That's what you need to show. No sooner you can show that, that means identity is a homeomorphism, and in a homeomorphism tau prime is a subset of tau, so tau has to be equal to tau. Okay, is it clear? So that is, so basically this is what you show, identity is a closed map. You need to show that. Okay, so is it clear what we need to show?
Yes, sir.
Okay, so please try to do it by yourself first.
Sir,
Yeah, please tell me.
so I do like identity inverse, which goes to tau prime. So we took an open subset U in tau, and which U is tau is subset of tau prime. So U contained a
One
U is,
minute. So identity inverse is a map from x tau to x tau prime. Correct? Now tell me.
yes. We take an U open subset U of tau,
Okay.
and we apply the identity map. So we get identity inverse map U to U. So we get U in tau inverse, which send
Oh,
to U.
you in tau inverse, that is making sense only when you know the identity map is continuous. Identity inverse map is continuous. Then only we can say that inverse image of identity inverse of open set will be open, right? Correct. This is basically what here you are using the fact that identity inverse is a continuous map. This is a fact you are using, right? Correct.
Okay. Yes, sir.
But that's what. But I mean, identity inverse. Why it has to be open? We need to show that inverse image of open set is open. Although you take the open set u from where? From tau dash, from where? From tau dash. The inverse image of u is coming to be, I mean, you need to show that inverse image u, it has to belong to tau, correct? Then only, we can say that uh, it is continuous map. Is it clear? You need to show that u has to be belongs to tau. Then only you can say the continuity. Is the argument clear?
So we can not send the identity inverse U to U
No, no,
as we send identity.
identity inverse you can send u to. There is no problem. That is correct. But what is the guarantee that u shall belong to tau? Because tau is a collection of subsets of x, right?
Yes, sir.
Yes. So why tau? I mean, why u will belongs to again tau, right? There is no reason apparently. Am I not right? Is it clear? Is the confusion clear?
Yes, sir.
Yeah. So please think and tell me. So basically, you have to show that identity map is closed map. That means you have to start the closed set, and you need to show that image is closed. Okay, so that's why you need to show. Okay, so please try one more time. Sorry for the inconvenience. There is some technical issues. So am I audible? And is the screen visible to you?
Sir, you are audible, but the screen is not
Oh,
visible.
sorry, sorry. Wait, hold on, please. So now is the screen visible to you?
Yes, sir.
Okay. So yeah, so now continue from the problem itself, that how to show that identity is a closed map.
So we can directly show that as X is compact space. and identity is continuous map. So compact space sent to compact space as so identity is closed.
No, no, 1 minute, 1 minute. Repeat again.
The given is space is compact and housed out,
Mm-hmm.
and identity we get identity is continuous map.
Yes,
So we get a compare closed set to closed set. So we can show write like this identity is closed.
correct. So you're basically using the fact that domain is compact and codomain is also house drop. That's what you are using, right?
Yes, yes sir.
Oh, correct, correct. Very good, very good. So yeah, so it is telling that the identity is a closed map. Your argument is correct.
Yes sir.
Identity is closed. So that implies identity is a homeomorph. Now from this, how to show that tau is equal to tau prime? From the fact that identity is a homeomorphism, how to show the tau equal to tau prime? Please think about it. Is it clear what I'm trying to say?
Yes sir.
Yeah. Please think about how to show that identity is a closed map here. Sorry, identity is closed map, it is done. There is no doubt about it. So it's a homeomorphism. You need to show that tau is equal to tau prime. How to do it? So please think and let me know.
Sir, as identity is homeomorphism, so we can write identity inverse is also continuous.
Correct. Right. Then so identity inverse. It is from where to where? It is from x tau to x tau prime. It is continuous. Then
Audio sir.
then what?
Sir, no audio.
Oh, now is it coming?
Yes sir.
Okay, so yeah, you are correct. The ideal inverse is continuous. Then what?
So sir, we take image of U an open set which also is in tau prime. U belong to tau and identity inverse continuous map. So U send to U.
Hmm. So that means identity inverse of U has to be U and must be open. So U belongs to tau prime. We put plus equal
Yes.
to tau. Correct. Absolutely
Yes.
correct. So that means in a compact Hausdorff space, if the topology is comparable, then they has to be equal. That's the moral of the story. Okay. Now, the next problem is okay. So there is something called hmm, hold on a moment. Let me put the multipliers. So there is something called finite intersection property. So in metric space, I am pretty sure you have read these things. Is it? In metric space, I'm pretty sure you have read this finite intersection property. Is it correct? Or well, anyway, I will explain this, no problem. But I'm just asking. Okay, so it seems you have read it. Okay, so there is something called once finite intersection property. What it is telling is that a collection C of closed set of X is said to have finite intersection property FIP if every finite subcollection of C has non-empty intersection. Finite property means every open, every closed set, every collection closed set having a has FIP means every subcollection of C has non-empty intersection. That's what finite intersection property means. Is the definition clear or no? Not. Let me know. Is the definition clear or not? Let me know.
Yes, sir.
Okay. So there is a result. It's basically exercise that so basically it's a question. Show that X is compact if and only if free collection C of closed set of X having FIP has non-empty intersection. So that means what? X is compact if and every collection C of closed sets of X having FIP has non-empty intersection. This is by what finite intersection property means. Sorry, having FIP has non-dis. That means if you take any, if you take any collection C which has FIP, that means element, that means all members of C has non-unit intersection. If this happens, the X is common, vice versa. Okay, is the question clear? Is the
It means we have to show if X is compact, so FIP is non-empty, and if
no
FIP is
no
non-empty,
FIP
so
no no FIP no no what do you mean by FIP non-empty? If you take any collection, if this collection has FIP, then the intersection of all the elements of that collection C is non-empty. Is the
yes,
argument clear? Is the question clear?
yes,
Yeah. Now please try to do it by yourself. First, you assume X is compact, and then assume that for every collection C you have FIP. Then show that elements intersection of the elements of C has non-intersection. Okay, so please take your time. Rahul, are you able to figure this out? How to approach this problem? Rahul, are you able to figure this out? How to approach this problem?
No, sir.
So, basically, I'll give a hint first. Let's say,
Sir, I just thought a line
hmm,
as X is compact, so there exists open cover which cover X.
hmm.
So we have to show that intersection of all that open cover is non-empty.
No,
Arbit
then what you need to show? You question is what? Question is X is compact if and only if something happens, right? That means what? You need to assume X is compact and you need to take a collection C having FIP, and you need to show that this collection which you have chosen capital C, all the elements have to, if you take the intersection of all the elements of C, then intersection non-empty, right? I mean, you can have open core, there is no problem, but the question is what? Every collection. The question start with every collection, correct? So you cannot consider only single one thing. Is it clear? You have to start with no,
is
you have to start with the arbitrary collection C which have FIP, and then you need to show that collection satisfies what? Norm intersection. Is it clear or not? Let me know.
yes, sir.
Okay. Is it clear?
So sir, we can take any open subset collection of open subset of X and which has intersection phi. So we have to basically so, so we have to show intersection is phi as X is compact.
Please repeat again one more time.
Mm, As X is, if you took X is compact, so there exists open subset UI
Mm-hmm.
and we have to show intersection UI is non-empty.
Open, no, it is not open set. From where open set is coming?
Open set is
From where open set is coming?
we took
No, no, that's what I'm asking. From where this open set is coming? First tell me that.
any arbitrary set.
What the question asks for? What the question? Every collection C of closed sets of X, right? From where open set is getting you?
Oh,
So you have a collection of some closed sets which satisfy FIP, and then we show intersection is non-empty, right? So basically, the thing is X is compact. C be the collection of closed sets of F having FIP. You need to show that intersection C belongs to C not empty. This is what you need to show. Is it clear?
yes,
What
sir.
do we need to? Is it clear? Okay. So now please try.
Okay, sir.
Yeah, please try. Are you able to figure out how to approach this?
No, sir.
Okay. So basically the thing is, okay, see, uh, hmm. So we need to show that this intersection C is non-empty. That's what I need to show, right? So the basic way is to we have to assume the contradictory method. That is, assume that intersection C belongs to C is empty. Okay, assume it is empty. Okay,
Yes.
so no sooner assume this, that implies what? Union of C belongs to C, complement of C is whole of X. Correct? We are taking the complements, right?
Yes.
Yeah. Now consider the collection C belongs to C. This collection is an open cover of X, right? Correct?
Yes.
Now since X is given to be compact, correct? X is given to be compact, right? This implies what?
This implies C complement cover
This implies that X
finite.
is can be covered by finite subcollection. Call it this way. So that implies, take the complement, what will get? Null set is equal to intersection of Ci. Correct? Up to this much is the things clear? Up to this much is it clear?
Yes, sir.
So that means what? This collection Ci, this is a finite subcollection. This is a finite subcollection of C, and since their intersection is empty, that means what? This the collection capital C don't have FIP, right? Is it clear to you that this collection C don't have FIP?
And we are writing this because intersection Ci is empty.
Correct. Finite FIP means every subcollection must have non-index section, but there we are getting one subcollection having empty intersection. That means the collection capital C don't have FIP. Is it clear?
Yes, sir.
But that is the contradiction of to the assumption that C has FIP, right? It's a contradiction. So that means our assumption was wrong. That means intersection C, collection of C belongs to C, it has to be empty. Is the argument clear? Yes or no?
It has to be non-empty.
Ah, it has to be non-empty, correct. So is the argument clear? Yes or no?
Yes, sir.
Yeah, please take your time, let me know. And so this is one direction. That means we have assumed that X is compact, and we showed that every collection C satisfying FIP has non-intersection. Now we have to do reverse. That means if this property holds, we need to show that X is compact. So yeah, so please do think for the reverse direction, and this argument also please do think. Let me know if you have any doubt or any confusion. is the argument. Are able to figure out the reverse direction argument? Are you able to figure out the reverse direction argument?
No, sir.
Okay, so reverse direction argument is as follows. Hold on, please. So basically, so so we need to show the x is compact. Okay, so in order to show compact, what we need to start with an open cover of x. Correct. We need to start with an open cover of x. Correct.
Yes, sir.
And we need to show this open cover as a finite sum. Okay. Now U is open cover, so U alpha complement. This is a collection. We call this collection C. This is a collection of closed sets of x. Is it correct?
Yes, sir.
Okay. Now we need to use the reverse hypothesis that any collection of C having FIP has non-intersection. So now what we will do, now consider the intersection of U alpha complement. So this is first of all empty. Is it correct? This intersection is empty. The complement of U alpha, this intersection is empty. Is it correct or not? Tell me. Is it correct or not? Tell me.
How it is empty as it is the collection of closed set.
Because X is union of U alpha. So you take the complement, right? Is it clear now?
Yes, sir.
Yeah. So that means since it's all intersection U alpha non-empty, that means the collection C. That means this collection don't have FIP. Is it clear? Since the all intersection is empty, that means the collection C don't have FIP. Is it clear or not?
Yes, sir.
Since this collection don't have FIP, that means what? That means there exists a finite subcollection U alpha 1 complement dot U alpha 1 complement such that their intersection is empty. Is it clear? Since the collection has no FIP, that means what? We shall get a finite subcollection U alpha 1 complement daughter U alpha 1 complement such that their intersection is empty. Is it clear or not?
Why we took finite only here?
Because of FIP means what? Finite intersection has to be non-empty. So this collection C has don't have FIP. That means what? That collection C has at least one finite subcollection whose intersection has to be empty, right?
Yes, but in the above line in this screen,
Repeat again. Repeat again.
in the last line where you write don't have a phi p, where you written intersection u alpha complement equal to phi. So here we are taking arbitrary intersection.
Correct. and then
And
we are
where
considering finite intersection.
finite intersections.
Correct. It's clear.
Yes, sir.
Okay. So this equation take the complement gives what? Union of u alpha I is equal to 1 to n, that is equal to whole of x. Is it clear?
Yes, sir.
So we have done the both way. Is it clear or not? Let me know. So both way argument has been done. Are you able to figure this out or not? Please let me know. Take your time.
Clear, sir.
Okay, so is it clear? Am I right? It is clear, right? Okay, so that's good to know. Okay, so we can go to the next problem. The next thing is as follows. Okay, so we can go to the next problem. So the next thing is as follows. Let x belongs to x, a subset of x. 1 minute. No, no, this has nothing to do. Just hold on. Okay, so that's all for compactness. Now we shall start continuity. Okay, till now in compactness is everything properly understood by you or not? Till now is compactness is everything understood by you or not? Let me know. Please let me know whether everything is understood properly or not.
Understood, sir.
Okay. Okay, so So have you studied connectedness in metric space course?
No, sir, I haven't watched the videos.
No, no, I am not asking the video. I mean, have you not read metric space before in your college?
Yes, sir.
So there, did you not study metric space? I mean, did you not study connectedness in the course of metric space?
No, sir.
Okay. So tell me one thing, in the metric space, basically what you have learned?
In matrix space, we just learned the general definitions.
Okay, apart from that,
Nothing, sir. They are just definition, not the speciality of the matrix space.
general definition means does those that include continuity
Yes, sir. Continuity.
and then compactness not in the syllabus?
They are in the syllabus, but they didn't taught
Ah, I
us.
understand, understand. Okay, got it, got it, got it. Okay, okay, that's okay, no problem. Uh, so see okay. So since it seems nobody has read the matrices previously, so the first problem is that I am not going to give the definition today itself because the definition itself is quite abstract. Okay, so the intuition is connectedness that suppose intuitively the answer give the answer intuitively. Suppose consider the hyperbola x square minus y square equal to 1. How does this graph look like? This graph look like this, right?
Yes, sir.
So see, they are not, so this those two curves, these two curves are not connected with each other, correct? So in some sense they are disconnected. However, if you consider circle, they are connected each other. I mean, they are connected intuitively. Everything is every point things connected, right? So we can say that it's a connected. So one obvious intuition is that suppose we choose any point x and took any point y. So is it possible to get a path from x to y, which from so that we can connect two points via path? Is it so? For hyperbola situation this is not possible, but for circle situation if we take any 2 point we can get a path such that that can be connected within line of the space. Okay, so basic intuition of connected is that whether if we are given 2 points on the space x and y, and whether are we able to travel from x to y while lying staying on that space itself. So that is what by connectedness mean. Is the intuition clear?
Yes, sir. So we are basically trying to find a path.
Yes, that is the one of the intuition that we have to try to find a path. So that is what by intuitively connectedness means. Of course the definition is quite different, the abstract definition is different, but the intuition is you travel from one point to another point while staying within the space. I mean,
Yes,
can
sir.
you so that's what a connectedness means. Suppose we have two shapes, this and this, and suppose they are self intersecting. So if we have any 2 points between x and y, we can travel from here to here and then here to here to join from this and this, right? So that means we are able to get some path from these 2 points. So yeah, so that's what by intuitively connectedness means. However, this notion of path, I mean, can you travel from one point to another point? This is something called path connectedness.
Yes.
Okay, that means you are you able to get a path or not. And the for general definition of connectedness, the definition is quite complicated. Okay, I'll give that too. So path connectedness mean basically, so path connectedness means For any 2 points x and y, here exists a continuous function f from what to where? X, sorry, there is a continuous function f from 0 1 to x, such that f of 0 equal to x and sorry one time, such that f of 0 equal to x, f of y is equal to 1. This is what by path connectedness means. That means if we have 2 points x and y, sorry, 2 points x and y, we shall get a path, we shall get a continuous map from x to y, which starts at x, that means t equal to 0, and ends at y, t equal to 1. This is what the path connectedness means. Is it clear?
Yes.
So, yeah, f of 1 is equal to y. So that's what path connectedness means. Okay. So the abstract definition. So the abstract definition of connectedness is as follows. X is said to be connected if only sets which both open and closed in X are empty set and X. So the definition is X is to be connected if only set which are both open or closed in X are empty set and the X. This is what by path connect. This is what by connectedness means. That means if a space is connected, that means empty X and the whole space X and empty set, the only sets which are both open as well as both closed. Okay, is the argument clear? I'm sorry, is the definition clear? I mean, okay, definition clear means do you understand definition or not? That's what I'm asking. Definition will be cleared after few 2 or 3 uh, things. Further, tell me, is the definition clear or not?
So how can we take if other than phi and x we get open and closed at both? So that set cannot be connected.
No, this is a definition. Now basically you want to ask that how the definition is coming with the intuition, is it right?
Yes, sir.
Okay, so for that there are a few theorems, then we get this definition is actually aligned with your intuition. Okay. So there is a definition, something called separation. So definition is a separation of X is a pair UV where UV are both open and closed in X such that their intersection is empty. So the separation of X is a pair U and V where this U and V are both open and closed and the intersection is empty. That means intuitively we have some we have some x, and in that case this this forms a separation. So that's the definition of a separation, because you are both open and closed, and of course they are separated, so their intersection is empty. Is this particular definition clear? What this definition is telling? Separation means we have a pair of subsets of x, each of which are both open and closed in x, and they have empty intersection.
Yes, sir.
Is the definition clear? Is the definition clear?
Yes, sir.
Okay. Now, the thing is, x is connected. Okay, so before this abstract thing, so look at the hyperbola x square minus y square. Okay, so clearly this piece and this piece forms a separation of this hyperbola. Is it clear from the picture?
Yes, sir.
Okay. So the definition basically what is that, so basically the definition is as follows. Sorry, let me give the theorem. The theorem tells that, I mean it's a theorem exercise, you can say x is connected if and only if has no separation. X is connected if and only if it has no separation. So yeah, so this is the thing you need to show. So that means what you need to do? By definition, connected means what? That means only set which are both open and closed in x, from or x empty. From that you need to show that it has no separation. So basically you need to follow the definitions. So the definitions of these two things are clear. Now please try to prove this theorem. It will not be difficult. Please take your time, figure this out by yourself.
Sir,
Yeah, yeah, tell me.
sir, we do like this. If X is connected, so the only open set is phi and X. Open and closed set is only phi and X. If we assume there exists a set A which is both open and closed.
Hmm.
So there also exist complements of A which is both open and closed. So A and A complement form a separation of X.
Correct.
So this implies X is not connected.
Okay,
So in this way we can
correct. What about the converse? It is correct only. What about the converse? Whatever we say is correct. Now, what about the converse? Please think.
the converse and not getting.
So, converse, you can use the method of contradiction. Suppose something not is true, that means the assumption has to be false in some sense. So, use the method of contradiction. Is it clear to you what I am trying to say?
So we have to choose X is separated. It is given X is not separated, but we have to choose X is separated.
So for converse, what we need to show actually first tell me.
For conversion, we have to show X is connected.
Yes, that means we can assume that X is not connected, and we can show that X has some separation. So that is the contradiction. That will come as a contradiction. Is it clear? I mean, is the target clear? Why we can do it by method of contradiction? Okay, in that case, please think and let me know in the next session. Today it's over 2 hours. Okay. So please try to think about in home the why this method of contradiction will work here. Okay.
Okay,
So
sir.
we shall meet in the next Sunday. Okay. Bye.
Sir,
Yeah.
there is a doubt. Sir, in the last
Okay.
session we didn't.
Can we discuss in next session? Okay. So whenever you have doubt on the
No,
joining
sir.
itself,
This is a
please
query
tell me.
about the email. We didn't receive the email of the last session, so we missed the last session.
So email regarding last what?
This is the third session.
Yeah. Yeah. Correct. Correct.
I attended the first one and second one I missed. The email I didn't receive the mail.
Oh, that's okay. I mean, sometimes I also did not receive any email. So in that case, you have to log into the portal, and in the announcement section, you have to check. In the announcement section, everything is there. Actually, sometimes due to maybe technical issue, we did not get the email. I also sometimes did not get the email of the other course. In that case, I have to check the announcement section. In the announcement section, everything is there. They send everything in the announcement section.
Okay, sir.
Okay. Okay. See you. Bye. We
Bye.
shall meet on the next session.
Thank you, sir.